Okay, so I'll announce our next speaker while he's setting up. So this is Joan Bruna. Joan is a professor at the Courant Institute at NYU and is also a visiting scholar at the Flatiron Institute. He spent time at UC Berkeley as a faculty member and Facebook AI research as a postdoc and visiting scientist. His PhD is from École Polytechnique, and he is the recipient of many awards, including the Sloan Fellowship, the NSF Career Award, and several Best Paper Awards. Joan is an expert on the theory of deep learning and its application to computational sciences. Today he's going to talk about the dynamics of deep learning models.
Okay, great. Thank you very much for the introduction, and thank you for sticking here for the afternoon. So yes, I'm going to talk about some topic that the title might already inspire some of the people here in the audience, and hopefully trying to stay true to the spirit of the workshop. That is, maybe there are some questions out there in AI where mathematicians can still have some interesting role to play. And I think I'm hoping that give you a little glimpse of that in this particular story. So this is a joint work with two excellent collaborators. So Margalit, she's a postdoc at MIT. And Denny is a colleague at Flatiron at NYU, soon to be faculty at Oxford. All right, and so my talk is really not about fancy transformers, very large thing. It's really old school neural networks of the ones that you see here that have already many years old. And this family of neural networks, they are, I would say, like the natural first step if you want to understand maybe first order problems or challenges in understanding how mechanisms of learning and operating these networks, right? And sometimes they are the simplest idealized model to understand like this phenomena, this mystery, what we call feature learning, right? This idea that these neural networks, we feed them a lot of data, and somehow they find their own ways to extract information, right? And so this is maybe the simplest model where we can understand this phenomenon. Okay? And the folklore is that so this neural network, the advantage is it has essentially just one hidden parameter, which is how large can I make it, right? How wide can I make it? And the folklore is that these large neural networks, they typically give us the best trade-off, right? At the end of the day, ultimately, it's better to make neural networks wider if you really want to get good performance at the end. So in some sense, this talk really is about comparing. It's really about this question, right? So in this neural network, it just so happens that here I have something that I can implement in my computer. I have, I would say, maybe 1,000 neurons, and I can try to understand what happens with this model. But it turns out that there's some kind of idealistic model sitting behind this finite neural network, which is the same thing, but now I'm just going to pretend that I have infinite number of neurons, right? So somehow this is more like a mathematical construct. Okay, and this talk is really about, can I understand what happens here in this algorithm by understanding what happens here? Okay, and how can I make this back and forth of transferring information? Okay, and so the starting point is what I hinted at in the previous slide is something that is very natural, like a change of perspective that it happened very often, many years ago in physics and many areas of mathematical physics. And here in particular is really the point that I can view this shallow neural network as something that is parameterized by the positions of m neurons. And I can view these m neurons as m particles, right, that are evolving in some domain, right? So this could be the parameters of my 5 neurons in my model. So I can alternatively express the state of this system by the empirical measure, I can just put a bunch of Diracs on top of these positions and build this empirical measure, and now express this average as just an integral against the empirical measure. Okay? So suddenly it's just really just a reparameterization of the problem, right? Instead of looking at where the positions of the neurons are, now I'm just going to keep a state of the density of, for every point in my parameter space, do I have mass or not? And now what do they gain? Well, here I have an expression of the problem that is very nonlinear, right? So this activation function here, rho, is a nonlinear function. Now, if I look at this expression here, and my variable now becomes this measure, now I have a linear dependency between f and the measure. What it means is in terms of the loss, right, the objective function, before, if I look at this problem, at the level of the parameters, this is a potentially very complicated objective, right? It's very non-convex, and Gerard has studied a lot, kind of questions of complexity of these kind of landscapes. But if I now look at these laws at the level of my measure, now it becomes, at least if we want to look at it from the distance, it looks like a quadratic problem, right? So I have some kind of convexity to hold on into. And so this is something that has been exploited and leveraged by many colleagues in the field, is that now I can re-express the training algorithm, right? The training dynamics of moving the neurons using, let's say, gradient flow here, just to be simple. I can now use this translation to look at the dynamics in that space, right? And the right way to think about them is that now the dynamics are what's called a Wasserstein gradient flow, which is just a fancy word to talk about what's called a continuity equation, right? Like a transport equation, right? Which basically tells me that the way this density is going to evolve in time is going to follow some instantaneous velocity field, right? And the right translation is that, this velocity field is exactly the gradient, right, like of the potential that comes from the original formulation. Okay, and so because I have now in a domain that I have a bit more structure, what we have is that if I look at the problem of understanding what happens with neural networks using this perspective, I can hope to get some notion of convergence, right? There's an appearance that I have been able to overcome the non-convex part of the problem and get something that looks like global convergence, okay? And this happens in the limit, what we call the mean field limit, or the thermodynamic limit, when the number of parameters goes to infinity.
So if you're set up with the general nu,
yes.
You're no longer restricting to having finitely many parameters.
Exactly. Now you can just forget about neural net and just view this as your PDE, right? And then try to understand convergence properties of this PDE. But it's true that indeed you really at the end, we care about being able going on the other direction, right? To understand how to go back. And that's basically what this talk is going to be about, okay? So the whole point is really how can we, in a sense, go back to the original point and try to bring back some of these guarantees to the finite problem that we care about. So first stop, right? Maybe a first initial observation is that somehow going from like if I have my space of probability distributions and I give you any probability distribution in that space, there's a natural way to discretize, right? To bring any question, any statement about probability distribution about a statement about the neural net. Because I can just take a distribution and just produce like a sample, like m independent samples. I just sample m particles, and I can build this empirical estimate, okay? And here we all know that I can control the error. Here I'm just going to care about the error of the associated predictions. The error is basically satisfy a Monte Carlo estimate, right? So the rate of approximation is basically always going to be of order 1/√m, right? This is just 101 statistics. Okay, so this is what I call like a static picture. Here there's no dynamics, right? I'm just taking a measure and just making it discrete. Somehow a more interesting question emerges when it comes to training, to dynamics. Okay, so if here I told you that I could take a measure and I can discretize it, okay? So the thing in purple is like a mathematical construct, right? It's an object that only exists in math, right? The green thing is the actual network, right? And so the question really about dynamics is what happens with the original error, right? And now I start training, right? So when I start training, starting from the empirical measure, I'm going to basically evolve in the state of distributions. And the natural question that, in some sense, is a classic question in the field of probability and interacting particle systems is what happens with these initial fluctuations, right? Are they going to blow up? Are they going to shrink? Are they going to be preserved? And many people contributed to this field, in particular, including here Gerard and Ophir had also like work around this direction. I guess also Dan Lacker here at Columbia is one of the main persons who is actually right now still very active in this question. Okay, so I hope the question now is become clear that somehow like the interesting question is really dynamic, right? It's like what happens with these initial Monte Carlo errors, how do they grow in time, right? And we can ask it in finite time, right, which is something that maybe someone in learning theory would care about, right? I want to have a guarantee that if I train my neural network for 1,000 iterations, I want my error to be small, right? And how many neurons do I need to put?
And the dynamics you're looking at here are these
gradient flows. Gradient flow, yes. Okay? And another question that is maybe a bit more academic, but it's also something that I feel fulfills our wish, thirst for understanding, is what happens with this error as one really integrates this system arbitrarily long, right? So this is what we call this uniform mean time propagation of chaos. Okay, do we have a hope to stay at the same rate? Okay, so the standard approach in the field to understand propagation of chaos is to invoke some kind of coupling, right? We need to somehow relate these two systems, right? The real system with the idealized system. Okay, and we need to think about some coupling. Okay, and one way to do that is to maybe allow me to cheat a little bit. Okay, so what the algorithm has, the only thing that the algorithm is allowed to do is to, at the beginning of time, I'm going to sample, and once I sample, I can run my dynamics. I can evolve the empirical measure. But let's pretend for a second that we do the opposite. Okay, we first run the dynamics starting from this idealized world of mean field approximation. And then at any point in time, I can take this measure and I can sample it from it, right? I can produce this red point. Okay, so what this here means to say is that we are just basically swapping the two orders of things. Okay, so now from what I told you from before, the error between this point and this point is going to be the function error is going to be of order 1 over root n, right? Because if I produce this empirical sample from nu t, right, I'm going to pay an error that is of order 1 over root n. So now the question is really, I have two empirical measures here. Is there a natural way where I can couple them? Okay? And so, in other words, how can I produce a good empirical good empirical measure of nu t? So a natural way to do that is, again, by maybe looking at this picture. Right? I can take this neural network that is a finite width, and I can take an infinite neural network, and I can pretend that I can take any neuron of this population, and I can embed it in the infinite population. Right? I can, in other words, I can view these dynamics in the Lagrangian perspective. Right? I have basically, ODEs. Right? I have a system of characteristics that, in one system, they evolve under the mean field dynamics, and the other one they evolve under the empirical dynamics. The only thing I'm doing, I'm just initializing them at the same point. Okay, and then just letting them run. Okay, so I basically. And so, again, not hard to see that now I have a natural way by just triangle inequality to control the error that I make between the actual finite neural network and the idealized mean field dynamics. By just triangle inequality, I pay 1 over root m that comes from this error, and then I have to pay for how much these two empirical measures differ from each other, right? And so the better they are coupled, the smaller this quantity. And I can just use a naive coupling that is just the coupling that comes really from the initialization, right? So here what it means is that if I understand how much these neural networks that start, these trajectories that start at the same point, I need to track how they differ over time, okay? And so this is basically now the object that we are going to be talking about for the remainder of the talk, right? And maybe in picture, so this is now my domain, my finite dimensional domain. I initialize a bunch of points, right? These are this initialization of my neurons. And there's one evolution that is the ideal evolution that is in purple, that is the mean field evolution. And then I have the actual evolution where basically now the dynamics here are the actual dynamics of the algorithm, right? And I'm just trying to understand how far these two curves can fall apart, okay, can grow apart. How does this error evolve over time? So the first thing is, obviously I can just, for tracking this error, I can track how this coupling evolves over time, right? I can just look at the time derivative, and because these two curves, they follow a characteristic equation, I have an explicit expression for the velocity field, right? I can just look at the difference between these two velocity fields. And the key difficulty that is, again, by no means a new observation is that when I'm exposed to potentials here that are non-convex, well, there's not so much we can say about it, right? Because if I look at this example, I have two particles, I put them here maybe at the top of this double well potential, and I let this thing evolve. What's going to happen? Well, because of the non-convexity, these curves can basically fall apart, right? The difficulty is that when I have non-convexity, these trajectories a priori, they are not going to contract. There's no reason why these things should contract, okay? And so the only thing I can do, in some sense, is leverage smoothness. It's the only thing that remains, right? Maybe these things cannot expand too quickly, right? Because this double well potential has a little bit of smoothness. So that's exactly what we can do, for example, by just using uniform Lipschitz, Okay? And so by uniform Lipschitz, we can easily arrive at this differential inequality that basically controls the rate at which this coupling can expand by the coupling itself, right, with some source term here of 1 over root n. And so this gives you the, I would say, maybe standard result, right, that says that if I just integrate this differential inequality, I can obtain a Gronwall estimate, right? I can look at the error that I make, right, with m neurons at time t has a form that, okay, it grows with some exponential dependence on time, and it stays at Monte Carlo rate. And in some sense, this could be a valid answer to the original question, right? Is that if you integrate the system for constant time, maybe this thing is not something that you care about, and you get basically 1 over root m, and that's it, okay? In some sense, this is already something that some works, for example, Andrea, Montanari, and Theodore, and others, they already leverage this kind of arguments for understanding, optimization of neural nets. But obviously, there's a big...
If you can use only Gronwall, you cannot escape this exponential.
Perfect. You are anticipating. Right? So basically, the point here is that this only works for problems that are easy, right? Where there's no there's no saddle point, right? Where you can escape easily, we can escape quickly, right? So if as long as you are forced to integrate these dynamics for times that are, let's say, polynomial in D or even linear in D, this thing is not going to be useful, okay? So the question is really now, I mean, that's kind of the motivation of this work is, okay, how do you do beyond Gronwall, right? Well, is there any hope to say something that goes beyond this estimate? Okay, so let's try to dissect a little bit further this coupling dynamics, okay? So what it means is that now let's focus on problems where we are talking about regression. Okay, so this instantaneous potential that I wrote, remember that this is like the first variation of the loss, okay, when you expect it at the level of the measure. And this decomposes naturally in two terms, right? One that is kind of the correlation term, which is, if you want in physics terms, this is like an external field. And then I have an interaction potential that tells me basically how two neurons are correlated, right? The correlation between two neurons. And so what we're going to define is just a quantity that we call the local Hessians, which is just looking at the Hessian of this potential when I track the position of every particle, right? So I basically, the idea is that here I would be tracking any particle along the mean field dynamics, and at any point in time I want to understand this, basically like second order information about this potential. Okay, this is what we call local Hessian. And then I also define the interaction Hessian, right, which is looking at the interaction kernel here and upgrading it to measure interaction between vectors, right, so that it can basically compare gradients, okay? And clearly this interaction Hessian is still PSD, right? Because I can still write it as an expectation over features. Okay? So another way to think about it, now if we dissect this coupling dynamics from before, remember that we could easily look at this term derivative of the coupling by just looking at the difference of the two velocities. So if we just use these two objects here, we see that somehow we recover something that maybe it could be interpreted as another interaction system, right? But now instead of talking about the initial particle, the initial neurons, now what we call particles are the fluctuations themselves, right? So it's kind of a second order particle interaction system where now they have a diagonal term that is this external field that is kind of this local curvature, and then I still have like an interaction term that is PSD, and then I have a source term, right, which is basically the thing that is pumping error, right, at the Monte Carlo scale. Okay? So now really the question is, yeah, sure.
So what is the expectations of J?
Oh, this is just basically this is I have an expectation of J here is just that I have it's just one. It's like a uniform distribution. At the beginning I have just basically an empirical measure that is 1 over m. So think about this as just like an average. So think about this. This is basically this dynamic for one particular neuron. What I'm going to see is like the average effect of all the other neurons averaged by this interaction. Okay? Yes. Okay. So basically now this is the quantity that I care about. So these are the linear dynamics, where again I have now, if I express it without coordinates, now there's no expectation, right? This is just a diagonal term. This is a diagonal operator. This is the PSD operator, and this is the source term. And so what is the structure that I have if I want to ever have any hope to do better than Gronwall? What I have as available structure is the fact that this object here is diagonal. and that this HT is PSD. So now, one important observation is a kind of the a key challenge, right? Is that these two operators, they do not commute, right? The HT in general is not diagonal, right? And moreover, it's not because this object here is PSD that suddenly it's going to help me, right? Naively you could say,
Positive semi-definite.
yes, okay? So you could argue that this, if being a PSD, might be a source of dissipation, right? It's always something that's going to do some dampening. But this is not true, right? In general, when it interacts with another operator that doesn't commute, this can actually create problems for us. So what we try to, the approach that we try here is indeed just to hold on to whatever structure we have that is really the fact that this object here is diagonal. Okay, and so what we think, you can think it in terms of introducing a baseline, like a different system, right, where there would be no interaction, like what we call this interaction-free dynamics. Imagine that you had like a system that would only evolving according to this law. This system now, this is commutative, right? So now you can integrate it explicitly, right? You can just compute the propagator of this system by just, just view these as scalars, right? You just do Gronwall, right? By integrating this dt, okay? And now you can use this baseline to represent the solution of the original system, right? And this is called the separation of variables at the Duhamel principle, right? You can just now express the solution of what you want in terms of this like interaction-free propagator, okay? And let me also say that this object that we introduced, this propagator, has a very explicit physical interpretation, right? So what does it mean? Basically, remember that these are the curves that we had, like this is the evolution of the mean field dynamics. So this object, what it's telling us, is like the Jacobian of these characteristics. It's basically, if I take a particle at time s and I apply some perturbation, I move the particle here a little bit. How is this little perturbation going to be felt later in time, at time t later on, right? So this is exactly what this operator is telling us, right? This Jacobian, okay? And why this is maybe a good idea? Well, you can see that this propagator leverages commutativity, is still aware of commutativity, right? If I now look at the norm of this operator, right, the log of this operator, you can see that it contains, it's the max of some integral, okay? Which is not the same as first taking the max and then integrating, which is what you get in Gronwall, right? In Gronwall, you integrate basically the worst case direction, right? And so this is really the key, the key source of what we can potentially gain, right? This is basically the key inequality of the whole talk, okay? All right, so how can we actually make this whole thing work? So we need some ingredients. We need some assumptions, right? This is not going to just, be a cheap gain. We need to understand some property. The first one, obviously, is that we are going to ask that this system that is simpler, that has no interactions, itself has to be stable, right? In other words, when we integrate pretending that there are no interactions, we don't want any blow up, right? We want this propagator to be of polynomial scale, okay? And why is this something that could be realistic, right? Is this like a realistic assumption to ask? We can get intuition for why this assumption comes to be by looking at what happens in dynamics that are univariate, right? And univariate dynamics, when you have transport equations in 1D, you get these very nice topological abstractions, right? In other words, if I have a probability distribution in 1D that evolves according to some continuity equation, the percentiles are preserved, right? If I move, if I just discretize this histogram and I just see how the histogram moves, right? The relative order of neurons in the percentiles do not change, right? And so what it means is that this Jacobian map, you can represent it, you can view it as a ratio between the two densities, right? I just, by definition, this Jacobian map is basically going to be obtained as the ratio between the density that I have at time s at one particular position and the associated density at time t, okay? And so this just gives us a natural way, but if you have systems where you can basically lower bound the denominator, you can upper bound this Jacobian map easily, okay? And these are systems that essentially this is a representation that is very useful for problems that have like this hidden low-dimensional structure, like the single-index models, for example, that Gerard and Okoj and Reza studied, or things that are basically problems that have a lot of symmetries, right, where we can basically hold on these kind of structures. Okay? The other ingredient that we need is some form of incoherence or delocalization, right? The idea that we need somehow this propagator of the interaction-free dynamics to be basically to interact with this interaction kernel, by to have this product of these two operators to be small in some sense, okay? And so the natural interpretation here is that when we are far from convergence, right, what happens with one neuron at initialization is not going to be much felt for any other neuron, right? Like whatever one neuron is doing at the beginning is not something that is going to change too much the trajectory of another neuron that is very far, right? And this is one instantiation of this idea of mediocrity, right, that Gerard made popular, okay? And the other ingredient is local curvature, right? The fact that at some point in time, when I'm approaching the solution, right, when I'm basically close to convergence, I might, I might hold into some landscape that locally has some convexity, right? The idea here is that this is an ingredient that is actually implies, so that requires the support of the target to be atomic, right? So think that the model is going to converge into some final solution that has atomic support, and so basically the idea is that around the support you have the potential has some curvature. And this is an assumption that has been used in other works by Leanic and us before in the past. Okay. Okay. So the point is that if you have these three ingredients, then we can essentially beat the Gronwall estimate, right? And stay at the polynomial scale. So we can integrate these dynamics for polynomial time and get a propagation of chaos that stays at the polynomial scale. Okay. And here you get this Monte Carlo rate. Okay. So this might sound obviously very abstract, right? I mean, this assumption. I mean, it seems that the real strength is are the assumptions, right? That are maybe too very strong. Okay. And just to show that they are at least not completely vacuous, we can apply them to what problems that I mentioned before, right? These single index models. These are targets that look like that, right? Like the target function is a function that secretly is a one-dimensional function. Okay. So if you have these kind of targets with a certain structure in the activation, just to make the mean field dynamics converge, then you can actually leverage this machinery and get this kind of desired result. Okay. Okay. So I don't know how much time I have left. I didn't check the time. Okay. Well, I might need maybe 10 minutes. Okay. So in the 10 minutes or so that I have left, I'm going to tell you about maybe, yes.
The time horizon is what you expect.
It's t. It's you can say it here. It's d to the k minus 2 over 2. And k star is this information exponent that was introduced by Gerard. Okay. So I want to tell you two things before I wrap. Is that first is there any hope where we can understand whether these assumptions can be weakened, right? Do we actually need all these assumptions? And the other one I want to tell you about is can we make these results uniform in time, right? Can we actually extend the horizon for as far as possible? Okay, and maybe to motivate why these two systems, maybe here's an experiment that I obviously now run. This experiment is much easier now with with GPT, with a codex, right? It's now something I coded in maybe half an hour. So these are just experiments that maybe convince us that there has to be there's something potentially more general at play, right? And this is an example where I play with target measures that are just non-atomic, right? So this is the target here. Obviously, this target is not atomic, and you can see that all the indicators of convergence just work perfectly fine, right? So here, maybe the most important plot here is this one. Okay, so here I'm looking at the error that the network makes, scaled by the number of neurons. Okay, so the lighter the color, the larger the neural net. So here you can see that the error certainly stays at the Monte Carlo scale. It even goes down, right? So you can see that we are actually beating Monte Carlo scale, right? And so despite being obviously not in the realm of our assumptions, right? And and so the first thing I want to tell you is really about this uniform in time result. Okay. Okay, and maybe just to context, so here let me emphasize that we are looking at the gradient flow dynamics, right? So here there's no noise, there's no diffusion in the equation, right? And in contrast, this question of uniform in time has been studied by many colleagues, Sylvia, De La Rue, Pavlotis. There's many, important references, even like Danlacker, that if you look at this question in dynamics that have a little bit of diffusion, let's say McKim-Lazov systems, right? Or let's say that you just do gradient flow, but you add a little bit of noise, right, into the neurons. Then you get you can use arguments based on like functional inequalities, like log Sobolev, etc., contraction arguments that help you later in the dynamics, right? That give you contraction. Here we don't have noise, right? We don't have this kind of access to these functional inequalities. Instead, what we rely, there's an interesting there's a kind of an alternative that we exploited here, that is to leverage a different assumption. That is the fact that these systems are gradient type, right? So the dynamics secretly, well, they are not secret. I mean, the dynamics are gradient type, right? So there's a Lyapunov function that is very natural, which is the loss itself. So when we have when the loss itself has sufficiently fast decay, algebraic decay, right? So it has to decay, faster than 1 over t squared. Then you can use the decay of the loss itself to kind of like replace, like as a replacement for this kind of like a contraction argument, right? And then you get uniform in time result. Let me also say, maybe this is for the experts, or just to give you a little bit of context, right? And so this is really like a non-asymptotic version. The closest that we have in the field is something that was developed by my student and my colleague Eric van den Eyden a few years ago. That was actually asymptotic and was relying on bad assumptions, right, on this interaction kernel. Here we don't have these kind of dependencies. And you notice here that there's something that we lose, right? So here we are not we are not at the Monte Carlo scale. This rate can be slower than Monte Carlo. And this is because we need to handle this higher order error term, right? There's a certain development, and we need to control higher order terms in the expansion. And this is why we need to pay a little bit.
This is better than Monte Carlo?
No, this is worse. This is worse than Monte Carlo, right? So at fastest is Monte Carlo, but then you can get slower whenever this rate is not sufficiently fast. Okay. And so, and let me add one point about this assumption, right? So this is obviously an assumption that it's hard to verify in general, but there are some examples where if you use it in interaction particles, like if you look at a kernel that is of this Riesz type, then you can get, if your target is sufficiently smooth, then there's this result by analysts like Maria Colombo and Leonic and Xavier Fernandez Real, where you can actually establish this asymptotic rate, right? So these assumptions are, again, not totally vacuous. Okay. And then let me now finally tell you a little bit about whether these assumptions are necessary or not. Okay? So remember that right now we had to rely on this like non-asymptotic result on these three properties. The stability, the fact that we have this kind of interaction-free system that was bounded, the fact that we have incoherence, and the fact that we have these like close to convergence, we need to have this local curvature. So right now, what we what we believe, and maybe kind of the correct picture, is that the real assumptions are the first two. Okay, so the stability and incoherence are real assumptions. And the number three is spurious, right? It's not something that we believe you need, okay? And maybe just as a first argument, to show you, maybe to convince you why we believe that these two assumptions are necessary, is that this is a very kind of clean and interesting example that shows you that you need to have actually both at the same time, okay? And so here's an example. It has the advantage that it's very explicit, okay? So here's a system where this interaction kernel is going to be the same or like constant, right? It's just a rank 1 interaction that is just going to average across all the neurons. And then as my the dt is just an operator that is going to be very sparse, right? And at every time, only one neuron is going to be active, right? And the rest of the time, the neuron is going to be doing nothing, okay? And then I'm just going to, first I'm going to wake up the first neuron for an amount of time that is log d. Then I'm going to wake up the second neuron, so on and so forth, right? And I just do it all the time like this, okay? So first, if I forget about this term, right, I basically have a system that I can very easily integrate. And because every neuron, every coordinate is only active for log d time, when I integrate, basically the propagator norm is exactly d, right? So the logarithmic norm is log d exactly. But if I consider the propagator, if I have the joint system, then if you use this like very simple like a Floquet calculus, you can explicitly also compute the norm of the propagator of this system. And then I basically suddenly get something that is not good at all, right? Because now as soon as I have a little bit of interaction, now the norm of this thing becomes, like the norm of this thing basically goes at the exponential scale, right? So instead of being a linear in D, now it's exponential in D. Okay, so the fact that you are adding this like interaction, even if it's PSD, it can really blow up the norm of the system.
You're adding something that calms everything down,
but it does it, but it's not. And the point is that it completely breaks commutativity, right? It's like whatever this neuron was doing, right? With there's no interaction, no one else cares, right? This neuron is just completely orthogonal to the rest. But now that I have interaction, the fact that this neuron has waken up is gonna mess up the other neurons. And if I do it again and again and again, I can just basically propagate the fluctuations up until they blow up. Okay? And so you need this kind of control of the incoherence. Okay? We need to prevent that. So I'm not going to say much more about what we are, but basically we have preliminary results. For those of you who might be interested, we can follow up offline. But basically we have now results that remove the strong convexity and just exploit these two properties that I described, right? The stability and incoherence. Okay, and now the next question, of course, is to make these assumptions a bit less abstract and to be able to maybe apply them to real systems that have no longer this atomic support and maybe have these more complicated structures. And then the other thing that we are currently working on is to extend these ideas to models, mean field models, actually mean field descriptions that are still useful in neural networks beyond shallow networks. And like mean field descriptions that are very popular involve residual networks and also transformers, the one that Alex was talking about. Okay, so I think I'm done. And so thank you very much for listening. And if you here are some references of what I presented, and then if there's any questions, happy to answer.
Things where, I have one hidden layer, potentially infinite, number of neurons. So how does this work in sort of the deep learning context where I can fix the width of the layer but have arbitrary depth? Would these results apply in this context as well?
So they do not apply as such because we are looking at one particular mean field description. But as I was referring in the last slide, one can actually set up mean field formulations of neural networks that are deep. For example, when the number of layers goes to infinity, right? So right. You can actually so some of the framework that is described here, in some sense, has some mileage also to be applied to resonance. But there's still some technical work to bridge the gap. But I think in spirit, yes.
Thank you.
Maybe I missed that you said. Yeah. Maybe I missed that you said this, but what do you mean by chaos here?
Okay, so maybe
in the propagation of
could
chaos.
Explain it better. But my understanding of chaos, right, is that chaos refers to the fact that at initialization the particles are sampled to be independent, right? They are independent from each other, and because we are going to train them together, they are going to lose their independence, right? They are going to lose their. And so the question in this problem, in some sense, is to what extent you can still recover some sort of chaos in the sense that if you just track like the marginal distribution of a subset of particles, they are going to really behave as if they were independent, right? And this is so here we are only extracting. We only care about how the function that they represent collectively, right? So we are only tracking the error of the function. This is what's called like the weak propagation of chaos. But the literature is interested in many, many fine-grained properties of these systems, right? So for example, if we tracked the empirical distribution of neurons, right, over time, how much this empirical distribution, like how much this joint distribution is of a product measure, right? That's a kind of a classical question in the field. I don't know if chaos comes from there. Yeah. Okay. I think so. Sure.
In fact, for these things, there is another approach which is a little ambitious technically, but since you succeeded, it might work. The one way is to look, so you said you can either sample and then evolve, or evolve and then sample. And the second thing, the sampling at the end does nothing, because it's just
Yes.
the real thing is you start from this IAD, empirical measure, you evolve, and then you want to compare to the fluid dynamics.
Yes.
So for that, there's one way which has proved to be useful in the old days of interactive particles, which is to climb, and you're looking at the fluctuations now. One way is to climb to the large deviation. So you have a large deviation, so you introduce the entropy. You have a large deviation for the initial thing, right?
Yes.
And that's just Sanoff,
Yes.
relative entropy. Then you evolve with this flow, and then you use contraction.
Okay.
You have large deviation. But then what you're after is, and which tells you that the probability that this end thing is far from the other one is tiny, exponentially small.
Right.
But what you want is something at a smaller scale. So typically this is done by you looking at the functional space at the second, the Hessian of this large deviation principle.
Yes.
Wave function.
Mm.
And this is what controls, when the minimum is not degenerate, which is the case here, what controls this one over Wootend thing.
Right.
And the factor comes from the norm of this Hessian.
Exactly.
Of this,
Yes. Yes.
and so, and in general, if you do it directly, you will get the one valid thing and exponentially blowing up. But since you know that
Yeah. It would be
doesn't,
very-
probably analytically it will be similar, but it is probably that just at this contracting now.
Right. Right. That's searching
has
for
a
control.
controlled gradient in infinite dimension.
Okay. Well, that's very
probably what
interesting.
you're-
Okay. Yeah, it would be very interesting. And at the end of the day, the story here is that there's something in this propagation of fluctuations that is commutative, and we are just holding into that, right? And so if we could express it at the level of this, like Hessian, maybe express it in this more abstract form, that would be very interesting.
The thing that would kill this approach is if your minimum was degenerate.
I see.
And it's not, because you start from IAD. Your initial
Okay.
sampling is IAD, so you cannot do that.
Okay. Very interesting. Thank you.